Hello everybody, welcome back. This video is on section 3.3, polynomial functions. We just finished sections 3.1 and 3.2, 3.1 linear functions, quadratic functions with 3.2. They are polynomial functions, but they're the simplest kind of polynomial functions. We are now studying polynomial functions of higher degree, and I'll talk about the word degree and what that means in just a bit. But let's start first off with power functions. Now there's a subtle difference between a power function and a polynomial function. Not necessarily all power functions are polynomial and vice versa. But I just want to talk about its end behavior. That's why the end behavior of a power function. And so what a power function is, something that looks like this. K x to the p, or whatever, where k and p are real numbers. They're real numbers. They can be anything. When we talk about polynomials, this is going to have to be an integer, a non-negative integer for that matter, for a polynomial function. But this could be a half. I mean, it's just a real number. It could actually be pi. But anyway, this is a power function. And what happens is the behavior changes, the end behavior, which is what we're going to talk about. The end behavior changes based on k and p. End behavior. End behavior means at the far end. Here I'm going to negative infinity and infinity. And I put this up now because it'd be hard to write all that. But so the end behavior changes according to k and p. And what's going to happen is the same thing is going to be true for polynomial functions. The end behavior will change according to it's actually going to be the leading coefficient and the degree. So here we go. What all this is I'm saying as x, if k is greater than 0, if k is positive and it's even, for example, 3x squared. Put in it. 3x squared would be 1. If it's even, what's going to happen as x gets really small, this is going to get big. Woo. All we're saying is it looks like that. As x is really small, the function gets really big. As x gets big, the function also gets big. That's if k is greater than 0, such as x squared. Here, let's do one like 5x to the 6th or something. That's a power function. Negative 5x to the 6th. If the leading coefficient is less than 0, then as x is, it'll look like this. As x gets hugely big, this gets hugely small, and the same thing. If it's odd, such as 10x to the 5th or whatever, it'll look like this, something like that. The point is, this is already written, meaning if x is really small, the function's really small. If x is really big, as x gets bigger, the function gets bigger. And then there's one more, an odd function when the leading coefficient is less than 0. The exact opposite is true here. Looks like that. As the thing gets negative infinity, it's huge. As the thing goes to infinity, it gets really small. So that's what we mean by the end behavior. This will be true for polynomial functions as well. And I put that up just because I thought those were going to be hard to write, it would take time on the video. Okay, that's power functions in a nutshell. Now what we want to talk about is purely polynomial functions. I'm going to erase this board right here. Polynomial functions. Definition. Let's see. A function such as f of x equals a n x to the n. That, by the way, is a power function. Plus a to the n minus 1 x to the n minus 1. No longer a power function. Plus a 2x squared plus a 1x x to the first. Plus x to the 0, or a to the 0. A to 0, x to the 0. So that's a polynomial function. 10x cubed plus 3x squared plus 12x. That's a polynomial function. we've been talking about this, on and on and on. A polynomial function looks like this, where a sub n is any real number. Actually, it could even be that could be a square root or an irrational. Is a real number. But now here's the difference between a power function and n is it's actually a whole number. It's a non-negative integer. How's that? Non-negative integer. Meaning it could be 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so that's a polynomial function. And now there's two definitions in here. And I'm going to rewrite that because I screwed it up a little bit. So I'm going to erase this board over here and rewrite the definition and then talk about two things. And the two things is it will lead to the same kind of table as this. So polynomial function. Ooh, my back is down. Function f at x equals a sub n x to the n plus n minus 1 x to the n minus 1 plus, and it just keeps going down. If n is 10, then this would be 9, 8, 7, plus dot dot dot. A2x squared plus a1x plus a0. Definition of polynomial function where all the a's are real numbers. They can be any real number at all. The n's have to be a non-negative integer, a whole number, anywhere 0, 1, 2, 3, a counting number plus 0. So that's what the definition is. And then there's two things. Degree of polynomial is n. We've been doing quadratics. They are second degree polynomial. I even defined that as such, and I said, I didn't define the word degree yet, but I think everybody just sort of understood they were second degree polynomials. Linear equations are first degree polynomial. So the degree of the polynomial is n, x cubed, and then also the leading coefficient. And t is a to the n. By the way, the only thing the only restriction is that can't be 0. Because if that was 0, then this whole thing would be 0, then it would be an n minus 1 degree. So that's what we're talking about. The degree of the polynomial is n, and the leading coefficient is a to the a sub n. And now you could go right to that this board that I had before, and if it's even, and if a sub n is greater than 0, and if n is even, the n behavior is exactly the same. So we're not going to redo that. I thought we'd do that in the power function. But there is some things to understand, and I think just one more table, and that's it. Is that right? Oh, a couple things about this, and then a table, I believe. The y-intercept. In any polynomial function, at most 1, there's 1 or none. At most 1. Or none, I guess I should just say 1 or none. There's 1 or none, because it is a function. So if it crosses it once, it can't cross it twice. The x-intercepts, at most, n. That means the number of the degree. The x-intercepts, the number of terms. Meaning max or min is the degree n minus 1. And that's at most. And so I'm going to put this into a chart over here, and I think that'll be this particular section. Polynomial function. And write some examples. Let's see, how did this chart go? Degree 2, 1 term, 2 x-intercepts. Okay, so degree, number of terms, number of x-intercepts. So I'm just making a chart here. So if the degree is 2, I should put an example. I should put an example somewhere. the degree is 2. Example, x squared plus 7, 7x, whatever it is, something like that. If the degree is 2, there is at most 1 term and at most 2 x-intercepts. Here's a graph of it. Oh, well, not necessarily that one, but that could be the graph of it. If the degree is 3, there's at most 2 terms and there's at most 3 x-intercepts. Here'd be a graph of it, like that. By the way, there A, the first leading coefficient, is greater than 0. There, the leading coefficient is less than 0. That's from the very beginning of this. That's where the pink stuff was. If the degree is 4, the number of terms, the most number of terms it could have is 3, and the number of x-intercepts, the most number of x-intercepts is 4. It could look like this: 1, 2, 3, 4. Yeah, back down again. 1, 2, 3 max and mins terms. If the degree is 5, by the way, here a sub n is less than 0. If the degree is 5, goes down, goes back up, goes down, goes back up, goes down again. 1, 2, 3, 4. At most 4 max and mins, and 1, 2, 3, 4, and 5. There'd be 5 x-intercepts. And it continues like that. Degree and coefficient. I think we're finished. Good luck. I'll see you in a little bit and do some examples.